This problem is asking for us to find the power dissipated by one of the R1 resistors. In order to work this problem, the first thing I would do is label all my known information. I know R1 is 400 ohms. I know R3 is 50 ohms. And so every time I see R3, I'll label 50 ohms. And I know R2 is 200 ohms. My voltage source is 12 volts. At first glance, this problem looks a little intimidating. But if you utilize the tools that we've taught you, you may see that it's actually not that difficult of a problem. We need to identify the nodes to better understand how these resistors are connected in series or where they're connected in parallel. So take some time to first identify these nodes, labeling each one appropriately. I have node 1, node 2, node 3. As I'm labeling them, I'm thinking about what I'm doing and how I haven't really split for any resistors in parallel at this point. So I'm keeping that in mind so that when I think about the circuit, that helps me visualize what's happening. Labeling the next node, we might see that, oh, I'm seeing a spot where I can go multiple paths. So that kind of gives me a hint that, okay, I'm going to have something in parallel at this point. So this is node 5. And I have node 6, node 7. Notice I have some multiple paths happening. Node 8. And then I realize I missed a couple nodes over here. So I'm going to call that node 9. And then finally my last node, node 10. Now that I have all my nodes labeled, I know that redrawing this circuit might help me better see what's going on. So I'll start with my power source, my VS, which is 12 volts. And then I'll move from node 1 to node 2. I see that there's only one path to get from node 1 to node 2, and that is over that 50 ohm resistor. And that is over R3, which is 50 ohms. Then I can move from node 2 to node 3, again with just one path, across another R3, 50 ohm resistor. Notice how when I redraw it, I label my nodes so I can keep track of everything. Then I move again from node 3 to node 4, across another R3, 50 ohm resistor. Then I move from R4 to R5, again across another R3 or 50 ohm resistor. So I know my end goal is node 7. I see that there's two paths. If I go from node 5 to node 6 to node 7, I'll pass through R1, which is 400 ohms. I'll make a pit stop at node 6 and then pass through R1 again, which is also 400 ohms, and then reach node 7. Then I take my next path and I see that I can go from node 5 to node 9 through R2, which is 200 ohms. Then I can go from node 9 to node 10, passing again through an R2 resistor of 200 ohms. And then I can go from node 10 to node 7, passing through another R2 resistor, which is 200 ohms. Now I'm back to node 7, and I know from node 7, I go to node 8 through one resistor of R3, which is 50 ohms, and then I'm back at ground. I can close my circuit out to ground. Now that I have this circuit redrawn, I see that it's not as complicated or as intimidating as I initially thought. I have a lot of resistors that are in series with one another, and I have a few resistors that are in parallel with one another. What I'm trying to find is the power across one of the R1 resistors. Because they're in series with one another, they're going to have the same current that passes through them. And because they're the same value, they're going to have the same voltage drop. And so I can just choose one or the other to solve that power for. I'll choose this first one right here. So I'm trying to find the power of this resistor. That's my goal. Now, in order to find the power, what I need to do is either find the voltage drop across that 400 ohm resistor or the current that passes through that 400 ohm resistor. I know that I can simplify this circuit even more by identifying that each one of these 50 ohm resistors are in series with one another. Even though this 50 ohm resistor is after this parallel portion here, I can see that it's still in series with each one of the previous 250 ohm resistors. So I can add those together and make my circuit a little bit easier to understand. I have 1, 2, 3, 4, 5 50 ohm resistors in series with one another. I can say that that is 250 ohms. Then I have my parallel portion of 400 ohms in series with another 400 ohm resistor, and 1, 2, 3 200 ohm resistors that are in series with one another. I can just add those together as one resistor and call that 600 ohms. And then I can look at my parallel portions and maybe write those to be a little bit easier to understand. Those two 400 ohm resistors will add up together to be 800 ohms. And those three 200 ohm resistors will add up together to be 600 ohms. Now this resistor circuit is a lot easier to understand. Again, remember, I'm trying to find the power at that 400 ohm resistor. So maybe writing it with 800 ohms might get me more information, possibly the voltage drop or the current that I can use in order to find the power at that 400 ohm resistor. So now there's a few routes you can take. You can either find the voltage drop across each of these, or you can find the current. I'll first start by finding the current that leaves the power source. In order to find the current that leaves the power source, I'll have to write the resistors on the circuit as an equivalent resistance. I know that the 800 and the 600 ohm resistors are in parallel with one another, and they're in series with that 250 ohm resistor. So I can say REQ is equal to my resistors that are in parallel plus my resistor that's in series with those that are in parallel. So my overall REQ is equal to 592.857 ohms. Now I can find the current that leaves the power source. So the current that leaves the power source is equal to 12 volts divided by 592.857 ohms, which equals 0.0202 amps. Now that I have that current, I know that I can find the voltage drop across the 250 ohm resistor, and then whatever's left over, the voltage drop across the 800 ohm resistor and the voltage drop across the 600 ohm resistor, because they're in parallel. So I can say the voltage drop across the 250 ohm resistor is equal to my current of 0.0202 amps times 250 ohms, which equals 5.06 volts. Then I can say that the voltage drop across the entire parallel portion, which is equal to the voltage drop across the 800 ohm resistor and equal to the voltage drop across the 600 ohm resistor, because they have the same voltage drop according to Kirchhoff's voltage law, is equal to 12 volts minus 5.06 volts, which is 6.94 volts. Now, knowing the voltage drop here, I can find the current that passes through that 800 ohm resistor. I'll call that current 1, which can then be used in order to find the power for that 400 ohm resistor. So I can find the current that passes through that 8 ohm resistor by taking the voltage drop, 6.94 volts, and dividing it by 800 ohms, because that is the resistance that I'm looking at and the voltage drop across that specific resistor. That gives me 0.008675 amps. Now I know that the current that passes through that 800 ohm resistor is 0.08675 amps. Through the first 400 ohm resistor and through the second 400 ohm resistor is that current. Now that I have a resistance value and a current value, I can apply the power equation and say the power for one of the R1s is equal to my current squared times my resistance. So if I have my current of 0.008675 amps squared times 400 ohms, I should get the power value at one of the 400 ohm resistors, which is 0.0301 watts. Now looking at my answer choices, I see that it's written in milliwatts. I know that there are 1,000 milliwatts in 1 watt, so I can convert that here and get 30.1 milliwatts, which is answer choice D. Now I do want to note that the route I took in order to solve this problem is not the only route that you can take. You could have used the other version of the power equation with V squared over R, or even I times V, and find the voltage drop across one of the 400 ohm resistors and then applied this equation to find the power. You could have taken different steps in order to get that information and you should end up with the same answer.